So we're ready now to convert spherical to rectangular, rectangular to spherical, and see if this picture will help us finish the whole thing, understand the whole thing. Are we ready?
Yes!
All right, good. So we're going to get into this.
Yeah, baby!
All right, so here's the story. We know from polar coordinates that x equals r cosine theta. That's a given. Now, here's the cosine theta. Here is the r, and you're saying, why is r rho times the sine of phi? Well, if I can imagine taking this little line segment here and putting it up here, you could then say that the sine of our angle rho is r over sine of our angle phi is r over rho. There, I said it right. Sine of phi equals r over rho. So, what does that mean? Well, it means this. Since the sine of phi equals r over rho, then solving for r, we got r equal rho times the sine of phi. Here is the r. Remember, just think about putting this r up here. So, y, from what we know about polar coordinates, is r times the sine of theta. And r, we already know, is rho sine theta. It comes from this equation right here. Keep in mind, this r would be up here. You know, you could get that another way if you wanted to. You could say, from this triangle, the green and red triangle here with a dotted line, you could say the cosine of pi over 2 minus phi is r over rho. But I would remind you that the cosine of 90 minus phi is indeed the sine of phi. Remember how cofunctions work? And so we still wind up with the same thing. So even if you just use this little triangle, you get the same result. So r is replaced with rho sine of phi. So therefore, if we're given spherical coordinates, we can find the x and the y. And the z, how about the z? That's this length right here. Well, cosine of our angle phi, maybe I should say sine of our angle phi, no, pi over 2 minus phi is this angle right in here, and sine of that is our z over our rho. But sine of pi over 2 minus phi is the same as cosine of phi. So cosine of phi is z over rho, so z equals rho cosine of phi. There, we've got it. Here, given polar coordinates rho theta phi, or rho phi theta, depends on whose book you're using, then we can find x this way, y this way, and z this way. Nothing to it. Now let's go the other direction. Suppose we're given rectangular coordinates. So if we're given the x, y, z, and we'd like to find the rho, the theta, and the phi. So what would we do then? Well, if we're given the x, y, and z, it's probably not very hard for you to see from the three-dimensional distance formula, distance from x, y, z to the origin is the square root of x squared plus y squared plus z squared. So therefore, that's our rho. That's one you probably already knew. Theta is the same theta as it is in polar coordinates. So you may recall that's the angle whose tangent is y over x, keeping in mind that if x is 0, then our theta is going to be either pi over 2 or negative pi over 2, and keeping in mind that if our x is a negative number, we're going to have to say something about adding pi to this angle arctan of y over x. And phi would be what? Well, phi is this angle right here, and if I called this angle phi, then this one would be pi over 2 minus phi, and I'd say pi over 2 minus phi is z, or sine of pi over 2 minus phi is z over rho. But sine of pi over 2 minus phi is the same as cosine of pi over 2. Sorry, cosine of phi. So what does that mean? Phi is the angle whose cosine is z over rho. I didn't write rho, I wrote x, y, and z, because after all, we're given x, y, and z. We're trying to find the rho, which we do this way, the theta, which we do this way, and the phi, which we do this way.